Hi everybody, Physics Ninja here, and welcome to my review on centripetal force problems. This is what we're going to do for you today. I've got 7 problems for you in total. They range from a whole variety of centripetal force problems. In addition to those 7 problems, within each problem there's several questions. Some of them are numerical, some of them are conceptual questions. So we've got 17 total questions to look at. So this is what I suggest you do. First of all, you go down into the description below and you go download the PDF of the problems. You try the problems out for yourself, and then you come back and watch the video to compare your solutions to mine, all right? And get the explanations also. So that's the key. You must try the problems before. If you just watch the video, you're going to learn very, very little. You learn a lot by putting it to the task, applying what you know, and determining what your weakness is. Then you can improve upon them. Okay, so like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. All right, let's get started. All right, here's the first problem. We have a ball of mass m, which is 1.5 kg, suspended from a rope and travels in this horizontal circle. The circle has a radius r of 1.8 meters, and the speed of this ball is constant at 3 meters per second. Our first problem says, what is the horizontal component of the tension force, called T horizontal? So this is what I suggest we do. We draw the forces, and they're already on this figure, so that is helpful. So my tension here is along that rope. This is a snapshot at a particular instant in time, and the weight is straight down. Now, what you should do here is we should choose a coordinate system where we have one set of axes that is along the direction of the acceleration. And for an object going in a horizontal circle like this, this is the direction of the acceleration. It accelerates toward the center of the circle. So guess what? I'm going to choose a set of axes that looks like this. Positive x at that instant in time points toward the center of the circle, and the y direction points upward like this. Now the other thing I'm going to do is I'm also going to define this angle here, theta, over here. Okay, so what we want to do now is break the forces down into components. So this is what it looks like, right? Remember, you have your tension force here that is at an angle. That is the tension force. The tension can be broken down. It has this horizontal component that I call Tx, and it has a vertical component here that you call Ty. Now the angle theta that I've defined, if I go up here, the angle theta here is with respect to that vertical. It is also this angle right here. So from this diagram here, you should be able to write that Tx is equal to T sine of theta, and also that Ty should be equal to T cosine of theta. So what we're looking for here is the horizontal component. That is this guy, Tx. So what we do now is we apply Newton's second law. So we're going to add up all the forces here in the x direction. In the x direction, that is the direction toward the center of the circle. Okay, there is only one force toward the center of the circle. That is my Tx, which is also T horizontal here. I'm not going to write horizontal. It's just a little bit too long. If there's only one force, that must be equal to mass times the acceleration, except the acceleration now is our centripetal acceleration. And the formula for centripetal acceleration is v squared divided by r. So let's go see. I think we know everything in this problem, so all you have to do now is substitute our numbers. So we get our mass is 1.5. My speed was 3. I square it, and then I divide by the radius, which is 1.8. All right, we put that in a calculator, and we should get a Tx value that's equal to 7.5 newtons. All right, so that is choice B. B is the correct answer for this choice. Now the next thing they say is, question 18 down here says, what is the length of the rope? All right, well, the length of the rope is denoted by this length over here. Well, what we can do is we can do a little trigonometry over here because we know the radius, so we should be able to write that the sine of the angle theta is equal to what? Well, it's the opposite over the hypotenuse. The opposite is r over L. I already know r. What I need to do now is I need to determine what is this angle theta. In order to do that, what we're going to do is we're going to use a combination of Tx and Ty in order to find that angle theta. So remember, we have our first equation here, which is the Tx equation. And Tx you can write as T sine of the angle theta. All right, so that is going to be what I call equation 1 right here. Let me go ahead and box that equation. Now my other equation that I'm going to need is I'm going to look at the forces here in the vertical direction. In the vertical direction, you should be able to convince yourself that the forces must sum to zero. There is no acceleration up and down. This object is simply going around in a circle. So that means that Ty minus mg must be equal to zero. Okay, well that means that, let me just bring Ty on the other side. Ty by definition is T cosine of theta. And that there must be equal to the weight of the object. This is what I'm going to call equation 2. Let me go ahead and box that equation up. Now my goal in all of this was to determine theta. If you know theta, you go back to my trigonometric identity over here, and I'll be able to find the length of the rope. So how can I get theta from equations 1 and 2? Well, one way you could do that is to take equation 1 and divide it by equation 2. If you do that, you're going to cancel out the tensions. You're also going to cancel out the masses on the left-hand side here. So we're going to be left with v squared over r divided by little g is equal to, again, it's sine divided by cos. Well, this here is tangent of the angle theta. This allows me to find that angle theta. So right away, you can find that the angle theta is the inverse tan. And now we substitute some of these values. This is 3 squared and divided by 1.8 multiplied by 9.8. All right, I put all those numbers in the calculator. I get an angle theta for me that was approximately 27 degrees. So now I go back up here. The question was, what is the length of the rope? Well, let's rearrange this top equation right here. Let me get rid of this. So my top equation then says that the length is r divided by sine of theta. So the r value is 1.8 meters, sine of 27 degrees. I put that number in the calculator, and I should get a length of rope that is close to 3.96 meters is what I got. And that also corresponds to choice B. All right, kind of a good problem, involves kind of writing down Newton's laws and determining the unknowns based on Newton's laws. All right, let's go to the next problem. All right, here's problem 2. We have a metal bucket with a mass of 1.2 kg. The water has a mass of 7 kg, is swung around a vertical circle. We're given that radius. We neglect the mass of the rope. The tangential speed of the water bucket varies around the circle, but is such that at the top, the tangential speed is just high enough. So the speed is just big enough to keep the bucket moving in a circular path. Okay, so first problem we have is the weight of the bucket plus the water and the tension in the rope when the bucket is at the top of the circle, T top, form a Newton's third law action-reaction pair. All right, so which forces are we comparing? Let's look at a free body diagram when you're at the top of the circle. So here's my bucket. All right, the total weight is the weight of the water plus the weight of the bucket. I'll just split it up. The weight of the water plus the weight of the bucket. Guess what? The other force acting on it is the tension due to the rope, and that's acting right here. I call that T. Now, do these two forces here form action-reaction pair? For forces to form action-reaction pair, we need 3 criteria. First of all, the forces, forces, let me just write this down, must be the same magnitude. Okay, we don't know if these forces are the same magnitude. Second criteria for forces to form action-reaction pair, they must be in opposite direction. Are these forces here in opposite direction? No, they're in the same direction. They're pointing down toward the center of the circle. The third criteria, which is very, very important, is they must be on different objects. These forces are both acting on the water and the bucket. So this here must be false. All right, these do not form an action-reaction pair. The next problem says the minimum tangential speed of the bucket at the top of the circle. All right, so to work on to finding the minimum tangential speed, what we have to do in this case here is, well, the minimum is going to be obtained when the tension here goes to 0. Okay. If the tension goes to 0, you eliminate it from that free body diagram. Now, for it to go in a circle, we need a force acting toward the center of the circle, and that here is going to be the total weight, which is acting down. That's toward the center of the circle. So what do we do now? Well, we apply Newton's second law to this problem. We add all of the forces here toward the center of the circle, and they're equal to the mass times the acceleration toward the center of the circle. The right-hand side here is simply the mv squared divided by the radius here. What is the total force acting down? That's the total weight, which is what? Well, it's the total mass, right? I'm just going to call this mass total times little g. And that must be equal to what? Again, this side over here, the mass is also the total mass. So we have total mass really on both sides. Therefore, what can we do to simplify this expression? You simply cancel it out. And really, we're finding the minimum speed. It can definitely go faster. If it goes faster than this value, it means the tension is no longer going to be zero. So now we simply get our expression here for the minimum speed. You bring the r on the other side and you square root of everything. So you get g times r. So my v minimum, 9.8 for little g. And the radius was 0.75 meters. All right, I substitute that in the calculator, and I should get a minimum speed here, which was equal to approximately 2.71 meters per second. All right, so that there corresponds to choice E. All right, next question says, what is the tension in the rope when the bucket is at its lowest point? And here we're going to assume that the tangential speed is bigger, right? 6.55. First thing I suggest is doing a free body diagram. So this is what we have. We have the weight is m total multiplied by little g. I have my tension force. Now when I'm at the bottom, the tension force is acting up. And we also know when we're at the bottom, the acceleration is toward the center of the circle. That's the centripetal acceleration. What we do now is I'm going to choose that direction toward the center of the circle to be the positive direction. All right, now we apply Newton's second law to this problem. So you add up all the forces. In this case, it's positive t minus the total weight, m total, times little g equals to ma. Well, again, the mass is the total mass that we're looking at, multiplied by the acceleration, which is v squared divided by little r. The goal now is simply to solve for tension. So you bring the weight on the other side of the expression. And if I factor out m total, I can write this as g plus v squared over r. I know all the values here, so I could just substitute the numbers. The total mass is 1.2 plus 7. Okay. And then the other term is simply the acceleration. The acceleration due to gravity, 9.8. And then plus the centripetal acceleration, 6.55 squared, that's my speed, and divided by 0.75. Put everything in the calculator and I get an answer of 549.4 newtons. That was my tension. Let's go see the choices. 549, that's close to 550. We're going to go with choice B is the best answer for this problem. All right, here's problem 3. We have a Ferris wheel that has a radius r and is turning counterclockwise at a constant angular velocity of omega. A student of mass m is sitting in the car labeled B, this guy over here. All right, at the instant shown, what is the magnitude of the force that the seat exerts on the student? All right, they're asking us for a force. Well, let's go ahead and draw the student here. So here's a student, let's say sitting down. All right, and it might be a backrest. He might be leaning up against the backrest. He might not. But let's draw all the forces. The student here has a weight, mg. What else? He's sitting down, so you should have a normal force from the bottom seat here pushing up on him. Now guess what? This problem says he's spinning at omega. If he's spinning at omega, guess what? It means he has some velocity over here. It also means he's going around in a circle at constant speed. Therefore, we know his acceleration must be toward the center of the circle. That means we need another force acting on him. Now, depending whether or not it's the seat providing him or maybe the frictions, the static friction between his clothes and the seat, there has to be some other force over here. I'm just going to call this one here static friction. All right, now let's think about these forces. It's what is the magnitude of the force that the seat exerts on the student? Well, let's think about all these forces. Which one are due to the seat? Certainly this one is due to the seat. And if the normal is due to the seat, then we'd also say that the friction here is also due to the seat. The weight is definitely not due to the seat, so I wouldn't include that one. So if you add both of them as vectors, this here would be the force from the seat acting on the student, right? How would I find the magnitude of that force? Again, I can use Pythagorean, right? Now, instead of substituting in things right away, let's look at our Newton's laws in order to simplify this problem, because all these choices here include the weight, and they include this term over here that involves m omega squared times r. So let's imagine applying Newton's second law to this problem. What would we have? Well, Fs is my centripetal force in this problem. If I add all the forces here toward the center, I only have one, which is Fs, and that must be equal to mv squared over r. Here's one equation. I'm going to call that the x direction over here. The other thing I have is, what about the vertical direction? In this case, when I add up all the forces, I better get 0. So I also get that the normal force must be equal to the weight. All right, so let's just go ahead and write that in my figure over here. So this force here is equal to mg, and this force here has to be equal to mv squared over r. Now, there is one other variable we need to introduce here, because some of these choices involve omega. One important thing to remember is, how is that angular speed related to the linear speed or the tangential speed v? We have this relationship equals r omega. You can't forget that. That means that my centripetal force down over here means the centripetal force, you can actually write this as m over r. And instead of writing v, I can write it as r omega and then square that term. So that means that this whole term here becomes m omega squared and multiplied by r. All right, so now what we're going to do is we're going to use Pythagorean, and we're going to simply sum the squares of the different components. So my total force from the seat acting on the student then should be what? Well, whatever the horizontal component is, in this case it's this, m omega squared r. I have to square that, plus whatever the vertical component is. The vertical component is the normal force. But we see that the normal force is also equal to the weight. So you can write it down as something like this. Right away we could see that the best choice here involves choice A. That is the correct answer for this problem. A little bit of a tricky problem. All right, the next question says, at the instant shown, what is the magnitude of the total force on the student? So they use this word total force. The total force is also the net force. When an object is going around in a circle at constant speed, if we know the acceleration is toward the center of the circle right here, guess what? It also means that the net force must also be in that direction, because Newton's second law tells us that. So we know this is toward the center of the circle, therefore the net force must be toward the center of the circle. Which of these forces is toward the center of the circle? In this case, it's that static friction force, but we said it must be equal to this here, m omega squared times r. So B is the correct answer for this choice. All right, a little bit of a more difficult problem, I think. Hopefully you got this one. All right, let's go to the next one. Problem 4 says a hollow cylinder with an inner radius of 0.18 spins around a vertical axis at a constant angular speed of 8 radians per second. A bug sits on the inner surface of the cylinder and does not move relative to the cylinder. The normal force of the cylinder on the bug is given as 0.035 newtons. The first question says, what is the mass of the bug? All right, if you're never sure how to continue these problems here, what I suggest is do a free body diagram. All right, here's my bug. Let's assume here that it's just on the side over here in this position. This is what the free body diagram looks like. I have mg acting down. What else? I have a normal force. They told me that in the problem. The normal force acts toward the center of the circle. And now there must be another force acting on it because it is not moving relative to the circle. It's not sliding down. So that force here that we should have is a force of static friction. Well, let me go ahead and fix that S over there. All right, this is what your free body diagram should look like. Now, in order to find the mass, what we're going to do is, well, we can write down Newton's laws and manipulate them in order to find the unknowns. So let's take that. When the bug is in this position here, we know its acceleration here is toward the center of the circle. So that means if you add up all the forces in that direction, I'm going to call that positive x. I'll call the vertical positive y, pointing up. Therefore, Newton's second law, you sum all the forces along x. In this case, there's only one force. It's the normal force. That must be equal to mv squared divided by the radius, which I'm going to call r. All right, so let's think about it. Here we have the mass, and that's what we're looking for in this problem. Do I know what the speed is? Well, I do, but indirectly. The value of omega here is given by 8 radians per second. But the value of omega is also related to that tangential speed through this expression over here, through r omega. You can't forget that. So we are allowed to calculate we are capable of calculating what that tangential speed is. The other thing we could do is do like we did in the previous problem, is just get rid of v by substituting it for r omega. So then this becomes simply mr multiplied by omega squared. So here I can get an expression for mass in terms of all the variables that I know. The normal force here was 0.035. The radius of that cylinder is 0.18. And then my omega was 8. And that's already in radians per second. So I substitute that in the calculator, and I should get a mass that is approximately 3.04 multiplied by 10 to the minus 3. And that is measured in kilograms. All right, that there corresponds to choice B is the best answer for this one. All right, if we want to prevent the bug from sliding, okay, what is the minimum coefficient of friction that we need? Well, if it's not going to slide, it means that our force of static friction here must be equal to mg. Well, the force of static friction, at least the maximum force, I can write it as mu s multiplied by that normal force, and we require this to be our equilibrium condition. Now, what do we know for the normal force? The normal force is given by my expression right here, which we already know from the value, but you can substitute it for this. So right away, you can manipulate this problem here in order to find what is this coefficient of static friction. It's simply mg divided by the normal force, n. We know all the values here now because we've already solved for the mass. We can use that value, so 0.00304 kilograms. We know little g is 9.8, and if we take our normal force to be 0.035, this is a condition for equilibrium. I substitute that in the calculator, and I'm going to get mu s, which is 0.85. Now, clearly, if it's bigger than this, you're going to be in equilibrium, right? But it can't be any less than this. So the best choice for this one was choice E down over here. All right, the next problem says, which of the following correctly describes the net force acting on the bug? Again, this is a uniform circular motion problem. If you know the direction of the acceleration right here, that also means that the net force is always equal to the mass times the acceleration. So the net force must point toward the center of the circle. Okay? So the best choice for that has to be choice C. The net force is not zero. The net force has at least one component that's in the tangential. No, the net force points purely toward the center of the cylinder. This is a centripetal motion problem. All right, here's problem 5. It says an aircraft climbs and then descends following a vertical circular path. The radius of that path is big. At the top of its trajectory, the speed is a constant 156 meters per second, and the mass of the pilot is 80 kilograms. So at the top of the trajectory, they ask, what is the magnitude of the force exerted on the pilot by the seat? So we have to consider our pilot here at the top of the trajectory. Okay, so that's in this position over here. Imagine he's sitting down. Well, he's going to have a weight acting down, mg. And if he's sitting, there's going to be some normal force acting up. The other thing we know is that if the circle is like this, we know that his acceleration is toward the center of the circle if it's a circular path. I am going to choose this direction here to be my positive direction. Now what I do is I apply Newton's second law. I add up all the forces in that direction, call that the vertical direction, and that must be equal to mass times acceleration, except the acceleration is my centripetal acceleration. So let's add up all the forces. I choose down to be the positive direction because that's the direction of the acceleration. So that means the left-hand side is mg minus n equals to mv squared over r. My goal is to find the force exerted on the pilot by the seat. Guess what? That is the definition of the normal force. So how do I do the normal force? I have to isolate it. So you bring normal on the other side, bring the mv squared on the other side. This is what the expression looks like. All right, we have m. I'm going to factor out the mass because it's in both terms. And then I get v squared over r like this. So now all you have to do is substitute our values. The mass of the pilot is 80. Little g is 9.8. And then the speed is 156. Don't forget to square that value. And then divided by this radius, 3308. That's already in meters. All right, I put those numbers in the calculator, and I got a value of 196. Let's just call it 196 newtons. All right, you go look at the choices. Clearly the best choice for this one is choice E. All right, so the next question says, if both the radius of that trajectory and the speed were reduced by a factor of 2, how would the force exerted on the pilot change? So let's think about it. So we started with R and V, and now what do we want to do? We want to cut R in half, and we want to cut V also in half. So let's see what happens to this expression here for this new normal force. I'll call it N prime. Well, this is the expression. The mass doesn't change. Little g doesn't change. So what happens to the speed? The speed is now v divided by 2. And I have to square that value. And now divided by, well, r divided by 2. All right, now you got to be careful when you evaluate this, but let's go ahead and do it. So mg doesn't change. And now what does this next term look like? Well, it's going to be v squared. And there's going to be, if you take care of all these factors of 2, you square this one, you take care of that other one, you should get something like this. Okay. So let's think about what this does now compared to my original expression, which is this one. What am I doing to that second term? I'm dividing by a number that's going to be bigger than that one. Okay? If you divide by something big, you get a small number. So I'm taking away less, right? So if I'm taking away less, it means what? That the normal force is going to increase in this case. Okay? You will find that the value of n prime is bigger than n. Okay? Because I'm subtracting a smaller number from the weight of the pilot. So it would increase in that case. Okay? N prime is bigger than n. All right, be careful when you work through the algebra there and make those conclusions. All right, here's problem 6. A child is playing with a new toy that consists of a ball of mass 0.87 tied to the end of the string. In this case, we know the length of the string is 0.3 meters. The child swings the toy above her head so that it moves in a uniform circular motion in the horizontal plane. The string here makes an angle of 63 degrees with respect to the vertical arm of the child. The first question is, what is the tension in the string? What I suggest is doing a free body diagram. Here's what the tension looks like. This is what the tension T is in that direction of the string. We also have the weight acting down, mg. What you should do in all these problems is break the forces down into components. This is what I'm going to call my Tx value, and this is what I'm going to call the Ty value. Now the angle theta here in this figure is going to be with respect to that vertical distance. So you should be able to write then Tx should be T sine of the angle theta, and Ty should be equal to T cosine of the angle theta. All right, now we could write down Newton's laws. We want to find T somehow. Well, let's write down Newton's laws and see what we get to. For this problem here, we know the acceleration here. When the ball is over here, the acceleration is toward the center of the circle. So I'm going to choose that direction there to be the positive x direction, and I'll choose positive y to be up. Okay? Okay, let's now write down Newton's laws. So what do? We say the sum of the forces along that center of the circle. In this case, there's only one. It's Tx. That's T sine of theta. All right, this must be equal then to the mass of the acceleration. Mass times the acceleration, rather. Mass times the acceleration, which is v squared over r. This is what we get. My goal is to determine t. What else do I know in this problem? Well, I know what the angle theta is. I know the mass. What else? I know the length. Now look I don't know the speed, right? And if you don't know the speed, you're kind of stuck at this problem. So this is not going to get us too far. So in that case, what we're going to do then is look at the other direction. And in that vertical direction, we know that the sum of the forces here must be equal to 0. It's not accelerating up or down. So this is what you get. You get Ty, which is T cosine of theta, minus mg equals to 0. Well, this equation is a little bit better, right? Because if you just rearrange it, you bring the weight on the other side. Think about what we know and what we don't know. We know the mass, we know little g, and we know the angle theta. So right away, you could write what that tension is. It's simply the weight divided by cosine of the angle theta. We substitute now 0.87 for the mass. We get 9.8. And then we divide by cosine of 63 degrees. Well, we put that in a calculator, and you should get a tension force here, which is approximately equal to 18.8 newtons. Go look at our choices. All right, choice A is probably the best choice. All right, look at the next question here. It says, say the tension in the string in the original problem is T, all right, our 18.8. Suppose the ball is now swung in such a way that the angle decreases. All right, let me highlight that. So the angle of the string decreases. So it's going to be in a smaller circle, right? The radius of the circle is going to decrease in that case. All right, the problem is, what is the new tension in the string? Well, guess what? My expression that I have over here is still valid. I'm just going to go ahead and I'm going to write it as T nu. T nu is simply the weight, that doesn't change, divided by cosine of this new angle. Okay, so that's my expression. Now the angle decreases. So what happens to cosine of theta nu? If I decrease the angle, I make cosine of theta nu, I'm going to make this term over here bigger. The biggest cosine of theta is when theta is 0. That's really decreasing the angle, right? So now if I make this bottom term bigger by decreasing the angle, that means I'm dividing by a bigger number. If you divide by a bigger number, it means that this new tension is what? Is going to be less than the previous tension that you had in that case. And what you could also do is simply substitute some numbers in here, but it doesn't matter what you do. At the end, you're going to find that T nu has to be less than T. All right, this problem down here says, say the speed of the ball in the original problem is v0. Suppose that we increase the mass of the ball, okay, but keep the length of the string the same. If we want the angle the string makes with the vertical to be the same as the original problem, what would the new speed of the ball have to be? All right, so this one you have to be a little bit careful. All right, so what we're going to do here is we need to look at, we want to keep the angle the same, right? So the length of the string is the same, L is the same, and they want the angle to be the same as the original problem. Let's find an expression for the angle of that original problem and see how it depends on the speed. So how can we do that? Well, I would go back to my equations. Here was equation 1 that involved the angle, but it also involves the tension. The other thing I'm going to do is I'm also going to use this equation right here, equation 2. So in order to get an expression for the angle, my goal is maybe to eliminate t, because it's not clear on what's going to happen to t. So what we can do now in this case is divide equation 1 by equation 2. If I do that, equation 1 divided by equation 2, this is what we get. We get equation 1, t sine of theta, equals to mv squared divided by r, and divided by equation 2. Equation 2 is t cosine of theta, and divided by mg over here. Let's see what we can cancel out. The tensions cancel out. The masses here cancel out. And what are we left with? You can see that this left-hand side is sine over cos. Well, that's nothing more than tangent of theta. All right, so the goal is to be, what is this going to be, this new speed? Well, let's get speed by itself. So what do? You have to bring r and g on the other side, and then take the square root. So this is what the expression for the speed looks like for the ball traveling at any angle. Okay, so what are we changing and what are we keeping the same? We've increasing the mass, but have a look at, there is no mass here. So it doesn't matter what you do to the mass, it has no implications here on the speed. If I'm keeping that angle theta the same, I'm keeping the radius the same because I haven't changed the length of the string, it means that the new speed has to be the exact same as the old speed, okay? You don't have to change it. All right, so that's kind of a good problem. All right, let's go to our last problem. All right, problem 7 says bicyclists are competing on a circular track that has a radius r of 58 meters. Assume that the surface of the track is horizontal. Bicyclist, whose mass is 58 kilograms, completes 12 full laps around the track in this amount of time, 240 seconds. The mass of her bicycle is 7 kg. Assuming the speed of the bicycle is constant, what is the magnitude of the total force exerted on her during the ride? Well, again, let's think about our free body diagram. All right, I'm going to try to draw a bicycle here. Here's a student riding her bicycle around the track. It has a radius r. Think about all the forces acting on that student and on the bike. What do we have? Well, definitely on the student, it's simply mg. What else? There is a normal force from the bike pushing up on her. And we need to have another force toward the center of the circle. Okay? There may be some static friction force acting in that direction. All right, we want to know the magnitude of the total force exerted on her. Again, the total force is going to be whatever the centripetal force is. So if you go ahead and you add up all of the forces here toward the center of the circle, I'm going to call this here the positive x direction. I'm going to call this the positive y direction. This is the total force acting on her. In this case, it's whatever this force is, Fs. That must be equal to mv squared divided by r. Okay, now we have to be a little bit careful. We want to know the total force acting on her. Okay, so which mass should we use right here? All right, the mass that you have to use right here has to be this mass of only the student. Right? We're not looking for the force acting on the bicycle or the bicycle and her. We're looking for the force acting on her. That's 58 kilograms is the mass of her. Okay, so that's very important. The other thing we need to do is we need to figure out what the speed is. In order to figure out the speed, what you need to do is simply look at, well, we're given this information. You do 12 laps in a time of 240 seconds. So think about what is the total distance divided by the total time. That'll get us our speed. The total distance is going to be the 12 laps, and the circumference of each one is 2 pi r, and divided now by that total time, t. So here I would just substitute by numbers. So I would get 12. Here I would get 2 pi. The radius is 58 meters, and my total time is 240 seconds. So right here, I'm going to get a speed of approximately 18.2 meters per second. Once you have that speed, now we could substitute into my centripetal force equation. So now what we do here is the mass is 58 only. What else? The speed is 18.2 squared. And the radius of that track, well, only so happens to also be 58. All right, so this is really the net force or the total force acting on her. You put that in a calculator and I should get a value equal to 332 newtons. All right, so I go ahead. That means choice C is the best answer if you're looking for the force acting on her. What else? What is the direction of the total force exerted on the track by the bicycle? All right, so this one you got to be careful of the wording also. It's the track, or on the track rather, by the bicycle. So the forces that I have here were the forces acting on her. Let me go ahead and clean up this diagram here. Okay, let's think about the normal force. I'm going to call N1 here, and we're going to call this the total weight acting down. All right, So that is going to be the weight of the bicycle plus the weight of the rider. That's the total weight. The force pushing up is the normal force, right? That's the ground pushing up on the wheels. All right, so this is ground on wheels. Call that N1. What else do we have? So on the bicycle tire, there has to be a force acting toward the center of the circle. I could call that Fs. Again, so this is what? This is the ground on the tire. Again, these are all the forces acting on the bike, right? What they are asking for is they want to know what is the total force exerted on the track by the bicycle. So which ones of these forces are actually exerted by the track? Well, it's the normal force N1 is by the track, and this friction force is by the track. So I could actually eliminate the weight here, because if I'm only interested in the forces from the track on the bicycle, it would only be the normal force and the force of static friction. Again, if you add those up as vectors, you should get a total force here that is in this direction. Now let's just go ahead and name this. This is the force of what? It is the track on the bike. That is the general direction. But now you go back to the wording. What they want to know is the force exerted on the track by the bicycle. In order to answer this one, what we have to do is we have to use Newton's third law to answer this. If the force of the track on the bike is in this direction, guess what? Newton's third law says that the force of the bike on the track is opposite, equal and opposite to that one. That is Newton's third law at work. So let's look at our choices here. What do we get? We get pointing toward the center of the track and upward? No, it's not. Pointing away from the center of the track and downward? This is a very good choice, right? That's what this force is doing. It has a component that's pointing away, and it has a component acting down. It's not only horizontal, so you get rid of those ones, and it's certainly not zero. So this one is quite a tricky problem just because of the wording. So be a little bit careful with the wording sometimes. Which force are they looking at? Certainly the force on the bicycle has to have a component toward the center of the circle, but the force on the track has to be opposite of that. All right, I hope you enjoyed this problem set, and I hope you are a little bit better at solving circular motion problems. We'll see you next time.